Welcome to Hartman Math. Today, the last day of my mini college week. Today, representing UCLA, my alma mater. We're going to talk about verifying trigonometric identities. Before we do that, a little bit of review of our basic trig identities from yesterday. Go ahead and simplify both. Pause the video here. All right, number one, we have Pythagorean identities, top and bottom of our fraction. So 1 minus sine squared theta is cosine squared theta. Cosecant squared theta minus 1 is cotangent squared theta. From there, we can get everything in terms of sines and cosines. So instead of dividing by cotangent squared, we can multiply by its reciprocal. And when we do that, the reciprocal, we could just use the reciprocal being tangent squared and then use a quotient identity there. And then our cosine squareds cancel. We're left with sine squared theta. Final answer. All right, number two, pi over 2 minus x. That sounds like a complement, so we must be talking about the cofunction. So the cofunction to cosecant is secant. The complement to this is x. So secant of x times cosine of x. And whether you turn this into 1 over cosine x or realize when you multiply reciprocals, you always get 1. Lesson 5.2, verifying trigonometric identities. We'll talk about what that actually is in just a moment. But here are some guidelines. Okay. Work with one side of the equation at a time. We're actually going to tweak that and say you're only allowed to work on one side. So pick the left side or pick the right side. You can only work on the left side or the right side. You have the choice. Things that you could be trying to do. Factor. If it says addition, try adding them together. Square a binomial. That one's a little tricky. Create a monomial denominator. Maybe something like conjugate, top and bottom. Those kinds of things. Look for opportunities to use the fundamental identities. Maybe try just do sines and cosines. Always try something, even if it doesn't work. It might give you some insight into what might work. Essentially, it's like a puzzle that we're trying to make fit together. All right, so what an identity is, it's an equation that is true always for all values of, in this case, theta. So no matter what theta is, it'll always be true. Like x equals 5 is not an identity because if we say x is 6, 6 does not equal 5. Okay, so it's got to always be true. That's an identity. To prove it, we're going to work on one side until it matches the other. And typically we want to work on the more complicated side. It's easier to take something complicated and simplify rather than to take something simple and expand it and make it more complicated. So we're definitely going to choose to work on the left side here. All right, so we had a couple things going on. Keep in mind, this is what our goal is. So I'm thinking with all this squared stuff, that could be a Pythagorean identity. In fact, it is. Cosecant squared theta minus cotangent squared theta becomes 1 by a Pythagorean identity. All right, so then we're here, and we've got 1 divided by tangent squared theta, cosecant squared theta. We could do the reciprocal on both. Flip this up as cotangent squared. Flip this up as sine squared. And then one of those suggestions was get everything in terms of sines and cosines. So maybe we turn cotangent squared, use the quotient identity, into cosine squared theta over sine squared theta. Keep in mind we were trying to get to some cosines anyway, so that was a good idea. And now our last one, we can cancel this out. Make sure you do take the last step. so that the left side matches the right side. So we've just verified that they're both cosine squared beta. Checkpoint. Go ahead and pause this video, see if you can show that this is a true identity. Work on one side, make it match the other. All right, looks like we have some odd-even identities. So here, secant of negative x, and secant's an even function. That's going to be the same thing as secant of x. Cosecant being an odd function, the negative is going to come out. It will be the opposite of cosecant x. And then from there, if we turn this into reciprocals, secant on the top is the same thing as cosine on the bottom. Reciprocal identity. Cosecant on the bottom is the same as sine on the top. We can drag the negative out in front. Negative, tangent x, and we got a match. Example number 2, verify. I'm dealing with some y's. I definitely think that the left side is going to be the more complicated side. So let's work on that. First thing I see is the addition. Let's go ahead and add these together. In order to add them, we do have to have a common denominator. We're going to need this as a factor. We're going to need this as a factor. So our first fraction is missing this. We'll multiply top and bottom by secant y plus 1. This one's missing secant y minus 1. We'll multiply that one top and bottom. So if we simplify that, secant y plus secant y, we get 2 secant y. We need that 2. The plus 1, the minus 1, they're going to cancel out. We should multiply these together. Difference of squares. And then secant squared y minus 1, that seems to be Pythagorean. If we look back on our Pythagoreans, I think we're going to see this is going to come out to be tangent squared y. Now, what are we looking for here as a goal? We've got the 2 in the right spot. The other stuff we got to work on. So remember, cotangent is going to be sine over cosine. I'm sorry, cosine over sine. So, in our next step, if we do reciprocal here, that sends cosine to the bottom. And then dividing by tangent squared y is the same thing as multiplying by its reciprocal. And that is cotangent squared y, which we've written as the quotient identity. All right, so we're going to get cosine y is going to cancel with one of the cosine y's. And then we'll have cosine over sine. And one more sine on the bottom. So if we split that up, get the canceling, a cosine over one of the sines, and the other sine goes there. Now we can easily see it, the 2, the cotangent y, the cosecant y. Example 3. Seems to be a lot going on the left. Let's go there first. I think we could factor. We got common factor. We've got clearly a cosine x that's a common factor. And then if we look at our sine of x, if we take the one with the lowest exponent, we could factor that out as well. And I think that would be sine to the 1/2 x. That's the lowest exponent. We could factor that out as a common factor as well. So we're going to factor out sine to the 1/2 x, cosine x. So what is left? Well, if we take and factor that out of the first one, that is the first term. So we'd be left with a 1. This times 1 makes that. minus, now here's the tricky part, we're factoring this out. Remember that when we multiply with like bases, we add the exponent. So 1/2 plus what makes 5/2? It would be 4/2, and we know that better as just 2. So it's going to be minus sine squared x, the cosine went there. We're getting close to where we need. Here's a Pythagorean identity. We can rewrite this one in root form. Raising to the 1/2 power just means take the square root of. And then just kind of rearrange with their multiplication. Multiply these together. And we've got a match. Cosine cubed x times the square root of sine of x. All right, go ahead and do the checkpoint. Pause the video here. See if you can solve our puzzle. Verify our identity. Make one side match the other. All right, here's what it looks like. We're going to use the conjugate here, working on the left side. The advantage of using the conjugate is it's going to turn this into 1 minus sine squared theta. That's going to lead us to Pythagorean identity. So if we multiply top and bottom by the conjugate of the denominator, we get 1 plus sine theta times itself, makes 1 plus sine theta squared. On the bottom, we do the multiplication, difference of squares, Pythagorean identity there. Then we're going to take the square root and the squaring undo each other here. And on the bottom, the square root of cosine squared theta is the absolute value of cosine theta. Essentially begs the question, why do we need absolute value here? And maybe why do we not need absolute value here? And the answer to that is in theta, and this time we do not have any restrictions on theta. We don't know what quadrant theta is in. So we know that when we take the square root with the square root symbol, we're only allowed to get positive answers coming out of that. So 1 plus sine theta, I think that's guaranteed to be positive. We don't need the absolute value because 1 plus sine theta is guaranteed to be positive because sine of theta has to be somewhere between -1 and +1. Well, at the lowest level, -1, if we add 1 to that, we're going to get 0. Not necessarily positive, but we don't need the absolute value in that case. We just get 0. Anything that's higher than -1, between -1 and 1, when we add 1 to it, we're always going to get a positive, so we don't need the bars. But down here, if let's say theta is in quadrant 2, cosine of theta would be negative. And we can't have this be negative, which is why we need the absolute value to surround it, to force that quantity to be positive. Example number 4. We got a lot of different functions going on here. Secant, minus cosine x, sine x, tangent x. I think our preference is probably to work on the left side due to the subtraction being a little bit more difficult to maneuver than multiplication. But with so many different functions, that could be, especially with nothing being squared, at least at this point, that's going to lead us to a Pythagorean, then we might want to go sines and cosines. So we work on the left and say, all right, we're obviously going to turn secant x into cosines, so that's a reciprocal. And we'll start there. Then perform the operation. Do the subtraction. We need a common denominator. So we're going to need to turn this into a fraction that has cosine as its denominator. So multiply top and bottom by cosine x. And then we're allowed to subtract them with a common denominator. And then there now we get a Pythagorean identity. So that's going to be sine squared x. And we've got one of the sine of x's that we need. And the other is, if we separate this, it's sine x times sine x over cosine x. And then this is just tangent, and we're good. Example 5. So this is one where I think it's probably going to be beneficial to work on the right side instead of the left side. Far more complicated over here. So we could do a lot of things. We could try sines and cosines. We could try conjugate for the denominator. Let's give that a shot, see if that works. The benefit to that is it's going to turn us into secant squared, tangent squared. And remember that secant and tangent are related by a Pythagorean identity. All right, let's see what we get here, multiplying it out. Cotangent beta times secant beta. And we get the difference of squares. This, I believe, is 1. So now we just got to see what happens here if we distribute. Cotangent beta times secant beta. Cotangent beta times tangent beta. The second one I'm liking because I know these are reciprocals, and when you multiply reciprocals, you're going to get 1. The only question is how we're going to get cosecant beta on this multiplication. So maybe we do go in terms of sines and cosines. And then when we do that multiplication, in this first one, the cosines are going to cancel. We're going to get 1 over sine beta plus 1. And then the 1 over sine beta, that one's our reciprocal identity, and we can turn that into cosecant beta. That's it for today. Good luck on your assignment. See you next time.